I'm Carbonell. Is this Dr. Elimination's office?
Yes, please. Come in. Have a seat. So, Miss Carbonell, what brings you here today?
Well, Dr. Elimination, I'm having problems in my current relationship with my leading group. It's Bromine. He's just so electronegative. At the beginning, he was so excited when he swooped in with all of his lone pairs. But now, our relationship just feels so polarized. I feel like he's just going to bond with any partial positive that comes around.
Well, it sounds like you already made up your mind about your bond with Bromine.
I have. I really have. I just don't know how to get him to leave.
Well, sometimes the best way to get out of a bad bonding situation is to bond with something new. A friend of mine, Dr. Addition, has a game show. I feel like it'd be a great way for you to meet some new leaving groups. If I called, would you be interested?
Well, if you think it'll help little old me.
Welcome everyone to the latest and greatest episode of Addition Elimination. I'm your host, Dr. Addition. Today we're going to be helping a Carbonell in a bad bonding situation find a new leaving group and kick her old one to the curb. Please give a warm welcome to Miss Carbonell. So, Miss Carbonell, tell us a little bit about what you're looking for in a new bonding partner.
Well, Dr. A, I'm looking for someone who can provide me with the electrons I need and who will be a stabilizing part of my life. According to my therapist, meeting someone like that would really be a driving force in helping me to get out of a polarized bond with my current leaving group.
And who's this with you?
This is Bromine, my current leaving group.
I have a lot of electrons, and the pK of my conjugate acid is -9. I'm not ashamed of it.
I see. Allow me to introduce our 3 bonding candidates. Dimethylamide, acetate, and alcohol. Alright, Miss Carbonell, now that we've met all our leaving group candidates, you get to ask them questions to place them on the ladder of reactivity.
Alright then, let's start with you, dimethylamide. You look a little sterically hindered. How do I know you'll be able to form a bond with me?
I have some methyl groups, it's true, but I have far fewer lone pairs than bromine, and can assure you that means I'm not going to treat you the way your current leaving group has been. You can depend on me not to jump ship the second I see some other positive charge.
How many lone pairs do you have?
Just one, Miss Carbonell, and I'm far less electronegative. The pKa of my conjugate acid is 35.
Some very sincere words from a leaving group with significantly fewer electron pairs and a much higher conjugate acid pKa. Let's cut to our mechanistic specialist to see how a reaction between these two would work out.
Well, Dr. Addition, this is how a reaction between Miss Carbonell, bromine, and dimethylamine would work. So first we have to look at the pKa values of the conjugate acids. We have HBr with a pKa value of -9 and dimethylamide with a pKa value of 35. This means that Br is more stable alone without you, while dimethylamide is more stable with you. Alright, so let's look at the mechanism. So the lone pairs from the nitrogen come in and attack the carbonyl and shift the electrons from the double bond to the oxygen. This is the addition step. And in the elimination portion, the electrons from the oxygen over here come in and kick off the Br-, leading to our product with dimethylamide.
Thank you for that. This bond looks like it could be promising. But is he really the best leaving group candidate for her? Where on the ladder of reactivity do our other leaving group candidates lie? Let's move on to our next candidate, acetate.
Alright, acetate, why should I choose you? It looks like you've already got a carbonyl, and you're still looking for someone else. How can I know that you won't go and react with some other partial positive?
Well, sure, I've got another carbonyl on one side, and some may call me a nucleophilanderer, but I prefer the term resonance stabilized. Stability is what you're looking for, isn't it? My ability to bond with another carbonyl should tell you that I've got what it takes to be your new leaving group. And if we're selling ourselves based on number of electrons, I've only got 2 lone pairs, so I'm still less likely to leave you than bromine.
I'm a little confused right now. I'm looking for stability, but I'm not sure I'm comfortable sharing a leaving group with another carbonyl. And he never mentioned his conjugate acid pKa. Miss Mechanistic Specialist, how would a reaction between us work out?
Well, Miss Carbonell, you're right to follow that gut instinct of yours. Just because the leaving group is more resonance stabilized doesn't necessarily mean that it's the right one for you. In fact, sometimes being more resonance stabilized means that it's better off without you. So So let's look again at the conjugate acid pKa values. HBr has a pKa value of -9, as you remember, and carboxylic acid has a pKa value of 5. So again, we see that Br- makes for a better leaving group because it's more stable by itself. And so we see that also a common reagent is sodium acetate. And we see that sodium can come off and just make this plus, while acetate is this negative. So let's look at the reaction mechanism. The lone pair on the oxygen come in and attack the carbonyl and shift the electrons from the double bond to the oxygen. And this is the addition portion. And in the elimination, the electrons move back down to reform the carbonyl and then kick off the Br-. And that is elimination.
Thank you very much, Ms. Mechanistic Specialist. We now know that acetate isn't Ms. Carbonyl's best option, but where on the ladder of reactivity does our final leaving group candidate lie? Ms. Carbonyl, are you ready to ask your questions?
Yes, Dr. Addition, I am. So, alcohol, what is your conjugate acid pKa? What can you offer me?
Well, Ms. Carbonyl, I'm a very simple leaving group. I've got one negative charge and a hydrogen. No resonance stability for me. My conjugate acid only has a pKa of 16, and I'm not sterically hindered in the least. I'd be happy to form carboxylic acid with you.
You do have a point about steric hindrance, but I'm not sure whether that outweighs your conjugate acid pKa. Ms. Mechanistic Specialist, what should I focus on?
In this addition elimination situation, we're going to be looking again at the conjugate acid with the lowest pKa value because, as we recall, it is the most reactive. So HBr again has a pKa value of -9 and water has a pKa value of about 16. So we see that Br- is still the most reactive and will come off easily. So looking at the mechanism, the lone pairs from the oxygen again come in and attack the carbonyl and shift electrons from the double bond to this oxygen. In the elimination, the electrons from this oxygen break down and reform the carbonyl to kick off the Br-, forming our carboxylic acid.
All right, Ms. Carbonyl, now that we've completed the ladder of reactivity based on the conjugate acid pKa's of all the leaving group candidates, including your current leaving group bromine, you're faced with a decision. Who do you choose?
I choose dimethylamide.
Congratulations, you two. I'm sure you'll make a lovely molecule. That's all for tonight, folks. Just remember, if you or another carbonyl are in a bonding situation with an overly reactive leaving group, there's a way out. Just follow this general addition elimination mechanism. In the first step, the addition step, have your new, less reactive leaving group come in and attack at the base of the carbonyl, sending your electrons from your double bond up to your oxygen. In the second step, have your electrons on your oxygen come right back down, reforming your double bond and kicking off your old leaving group, concluding the elimination step, giving you this final, more stabilized structure. You deserve a better leaving group.